Okay, so in the coming sessions, and we've had a little bit of a, when looking at the agenda, there is some bleed across between the different TFGs. So some of the talks are, a little bit arbitrarily allocated, but we've tried to sort of do it that way. This presentation is my attempt to at least begin looking at all the data that everybody's submitted. It's a tremendous amount of data. It's a real treasure trove, and I think I better get started. So I'll just very short on this case. The scale resolving simulations, these mean where we are looking to resolve the motion of the eddies in time and space. So they're inherently more computationally expensive, but we get greater accuracy compared to RANS methods. And because of the growth in compute power, these are becoming more and more used. They're pretty much industry standard in automotive CFD. And from looking at these two test cases, we want to go further than in previous workshops. We want to really try and understand why these differences in results are coming and really try and develop how much we'll learn from this. So this is my attempt to do that. We originally have stated these goals, particularly the cost-benefit analysis. It's a little spoiler, and if you've been taking part in the meetings, you'll remember a graph I dreamt up where we have cost on one hand and accuracy on the other axis, and that we try and put all the data there. Unfortunately, we aren't there yet, but we're not too far away. So there were 49 different people from 33 different institutions taking part. Not everybody ran simulations and provided data, but from those that we do, we've got a really wide variety of codes, and that's what makes this so interesting, because this just never happens, that everyone gets access to all of these the results from all of these different methods from the same test cases. So it's very exciting stuff. So in preparing the presentation, these are just some remarks on the decisions made and the thinking behind it. All of the plots you see I generated with the workshop dashboard, which has been put together by Astrid Waller with a lot of effort, also on behalf of Burkhard and Gary as the test case coordinators. So all that data that you submitted, which was in these big Excel files, has sort of been consumed by the dashboard, and it's now there for exploration. This is the link, but please, I think the link's been shared in Teams. Astrid asked me to say that it's just doing a bit of an update right now, so be patient and maybe look later on today or after the workshop. But it allows you to interactively explore all of the workshop contributions, and this is where obviously one of the powers is you can spot if we've maybe done something wrong or if there's some error. We've spotted in a few cases that there's maybe the reference pressure was wrong and things like that. We can come back to you and correct it. So a lot of it's there, but it's still a work in progress. And as said, I used it to generate all of the plots that I'm going to show. So what I'm going to do, another remark is in the presentation, I'm only using the anonymous partner IDs. It's obviously your choice if you want to keep them anonymous, so it's up to you to say, hey, I'm ID so-and-so. We're 28, by the way. But in the slides, they're all anonymous. I'm just going to sort of take a tour through the data, show you some of the things I found, and the emphasis is trying to understand what we're seeing. Where's this coming from the point of view of scale resolving methods? In doing that, and this builds on what Gary was saying, I've willfully ignored the force coefficients because you can get a lot of cancellation of errors, and they don't give a lot of insight. They don't really help you understand why. So starting with case one, and the base pressure, as Gary was saying, is very important for the drag. It pretty much dominates the drag coefficient. So we wanted to look here more closely. And this is something that Gary showed earlier, that RANS in the top bracket and scale resolving methods in the bottom bracket give very different shapes of the base pressure sort of topologies. and the experiment looks a lot more like the scale resolving. This is a result from previous workshops, something we knew. And then to make it a bit easier to cross-plot, what we did is we extracted this line across the middle here at Z.1944. That allows us to superimpose things over cross-plots. And as well as also started looking at the fluctuations, the RMS. So this is now all the contributions for case 1 divided into RANS on the left, hybrid RANS LES in the middle, and LES on the right. And what you see with the RANS is, as we've seen in the contour plots, they all share this incorrect or different to the experiment undulating shape. The scale resolving methods all or mainly give a good reproduction of the experimental shape. Some of them are a bit flat, a bit too flat. And what we also see is that the hybrid RANS LES tends to have a higher level of base pressure, whereas for the LES, the experimental data is sort of somewhat in the middle. So all of these plots have different y-axes. They're all sort of auto scale. So what you see is the black line kind of moves up as we go from left to right. But what we also see is that there's huge differences from case to case in the base pressure level. And this is one of the real things I'd like to get behind and certainly haven't fully understood yet. But yeah, sort of the median LES is closer to the data than the median hybrid RANS LES, which tends to be a bit above it. Thinking about, what's different between these things, the hybrid RANS LES is RANS on the car and only LES after the trailing edge separation, whereas the LES, if everything's working well, should have turbulent fluctuations in the boundary layer coming up to the shear layer. So perhaps that's an indication that what's going on is something to do with what I like to call the grey area in hybrid methods. So now we look at only hybrid methods and we divide them by grid. So we've got the G1, that's the coarsest grid on the left, the G2 and the G3. And there's an example of one contributor with the dotted line, that's contribution number 58. You can see as it progresses from coarse to medium to fine that, and unfortunately the color changes, that's just the way it is, but the pressure drops and drops as the grid is refined. And we see that for all of the contributions, which is interesting. Also, the one with a flatter shape, so this is the number 58 again, that becomes a lot more similar to the experimental shape as the grid is refined. So finer grids seems to improve things. That's not always the case. Looking at the fluctuations, obviously from RANS we get nothing or very little, and then on some of the I've flagged a few potential issues. So ID58, maybe the CPRMS has been processed wrong, and the same for ID49 on the LES side. And when I remove those, then yeah, what we see is that as Gary showed, the fluctuations are with scale resolving methods much closer to the experiment. And I think the LES in general looks closer in shape than the hybrid methods. Again, a wide variety of variation of the levels. So I'm going to speed up a little bit, but at the horizontal glasshouse plane, so this is this cut through here, we look at the surface pressure. And we started looking at this because we were looking for if there were maybe errors in the reference pressure, and this is a nice benign flat surface. And we see an awful lot going on. Yeah, so I'm going to break this down. We see some strong oscillations in some cases. We see some sort of dips in pressure near the upstream edges in some cases. So let's sort of dip into it. I think I'll gloss over this. This is just at the very leading edge. When we zoom in at this peak, we see that some of the data is scattered, and we think it's maybe because of the nearest neighbor interpolation when creating the slice instead of a actual on the slice interpolation. It's just an idea, and that affects IDs 59 and 2. So dividing again with RANS, hybrid RANS LES and LES. The plots are just too crowded, so we're going to break them down further. This is now RANS by different ID numbers. We see ID54 has these ups and downs in pressure on this flat surface. This is Remember, there's 2.5 degree yaw, so I think this is where the grid lines are kind of puncturing the surface. And this is a lattice-Boltzmann method. So my thinking is it's something to do with the immersed boundary-like way in which the geometry is captured. ID84 is on a body-fitted mesh, and we see a few wiggles near the on the sort of upstream of the corners. Yeah, near the leading edge corners, and we'll see a little bit more about those later. Now we're looking at Hybrand's LES and doing the same thing. So this is again ID84, and those wiggles have grown. So we get these sort of peaks in pressure near the and it's stronger on the finer grids, and it seems to be stronger with IDDS than it was with DDS. Yeah, I think that's just a remark, really. When we look at IDs 28 and 58, I wonder if the reference pressure is wrong for ID 58, and it's something we should look into, and we can correct this and update the dashboard. And then ID 54, again, this is a lattice-Boltzmann method. And we see, as for RANs, we see these oscillations, and we see that they vary with the grid refinement in intensity and in wavelength. With the LES, this is quite interesting. We see in all cases sort of dips in pressure, which we think is quite likely to be related to transition, laminar turbulent transition, which is obviously going to happen on this geometry at this Reynolds number. It's inherently physical, but what we also see is that its position changes a lot. So on some runs, it's actually quite at the peak pressure dip at the corner. Most of them, it's a bit downstream of the peak pressure dip, and it changes with the grid resolution. So on finer meshes, it tends to get a bit smaller, less intense. So it's inherently a physical phenomenon, but maybe it's being distorted a bit by grid resolution. And then we see, so the three plots on the left are all from sort of immersed boundary style approaches, and in all of them we see slight wiggles in the pressure. They have very different extents, some of them very strong, some of them rather weak, and on the body fitted mesh we don't see that. Yeah, so some more remarks. Okay, coming to case 2. One of the most interesting things to look at, and one of the most sensitive things, is the separation at the rear notch. So this is a view from above. So this is the rear window, and then this is the boot lid, and there's this notch here where there's a weak separation. Yeah, it's one of the most sensitive areas. I've also plotted the shifted CP that Burkhard mentioned. Everything's kind of zeroed. It's not zero, but it's collapsed at this measurement point 107 in the middle of the roof. That helps to make the plots so that you can really see the differences. We see quite a lot of scatter at the windscreen cowl, but also at this rear slant and notch region. And then something which I've noticed is, and these are our results, that's how come I've got the picture. We see a bit in this workshop, in our results for this workshop, we see a bit of a peaky pressure profile. And then when we look into it, the flow is indeed nominally attached exactly on the center line, but just to the right and left of the center line, we've got little recirculation things. So there's something interesting about the flow topology, because as you'll see, we get results that are grouped pretty much in flat or a little bit of a hat. I'm wondering if there's something bimodal, sorry to use that dirty word, in this flow topology. It could be that small changes in the setup could induce, maybe a coherent single recirculation zone, or this sort of double one. Yeah, just a thought. So all of the data there on CP on the roof line. Now just looking at the RANs, and this is what I mean. The RANs group very nicely into quite flat and so relatively separated, relatively attached, which is interesting. We're seeing on this green one, this is a lattice-Boltzmann method, we're seeing again some outliers, and I think that's related to the wiggles we saw on case 1. It's just that we're only sampling much less of the data. So we see the odd pressure point, which is quite far away for that for that code, and maybe it's basically that the fully sampled thing would have more wiggles, and we're capturing them quite randomly by the data points. Now we look at the hybrid methods. This is where it gets reasonably interesting from the scale resolving. We see some outliers. So this purple one here, which has a fairly early separation, I've been looking into it, and I think that what's happening is that the shielding function is breaking down, and I've got a couple of slides on that later. There's this one here that has a very high pressure. That's a lattice-Boltzmann method, and I think that it might be one of these pressure outliers again, that you can never really know. It might be, it might not be. So yeah, when we take those outliers out, we see again this grouping in reasonably flat or fairly curved pressure profiles. Looking at the large eddy simulations, again, we can comment on a few outliers. So this green and pink ones, these are sort of, I think, experimental runs to prove a point. They're with a higher order code, where the order of accuracy has been set to lower levels, third and second, and the results get closer and closer to the measurement as the order of accuracy is increased. So those, I think, don't need to be considered as, representative of LES. They're experimental runs that help us to understand how the methods work. And then what we have on these very sort of high pressure levels, this is interesting. These are wall-modeled LES being run essentially on hybrid RANS LES grids. So one of them is the committee mesh, and the other one is an emulation of the committee mesh with a similar resolution. So not enough resolution in the boundary layer for LES. And very interestingly, you see the same methods with hybrid RANS LES method activated, and the results get much closer to the experiment. So I think these are also quite illustrative. They say they're kind of like a sort of a warning, if you're using LES, you need to have the corresponding resolution. And then this shows quite neatly what happens, in an A/B comparison. So again, we can explain some of the outliers, and then things collapse much closer to the data. So I'm gonna skip a bit over the CF. So this year, for the first time, we asked for skin friction coefficient over the roof. And what we have, it's important to say that there is no experimental data. So this is just a Spalat-Almaras RANS, the black crosses. They're not truth, they're just an orientation. And we see a lot of the results sort of bunch around them. We see an outlier for one of the methods. The reason why I don't really want to dwell on them too much is that I've seen quite strong differences in the level, but they don't seem to translate to big differences in the actual flow topology, with a few exceptions. So as I said, should actually skip rather than just say I will. This is so this is back to this interesting point about the boundary layer shielding. This is two runs that were computed with a DDS approach. And one of them is on a mesh very much like the committee mesh, which has 8mm surface resolution on the roof and 4mm on the slant. And then on a second mesh that's much finer, 974 million cells, where the surface resolution has been reduced to 3mm and 1.5mm. And that brings us into the dangerous territory of shielding layer collapse in DES. And indeed, we see that on the finer mesh, the flow separates much earlier and goes further away from the benchmark. When we look at the skin friction here, I think it does tell a story, because again, we see this kind of confirmation that shielding function collapse is going on, because the skin friction starts to dip on the way up to the separation line. And so I think we have the famous grid-induced separation going on here. So I think that's a nice little story. I was always happy to find stories in the data. Okay, coming to the underbody leading edge, this is this area here. This is a snapshot from one of our simulations where the flow sort of separates from the lip. Burkhardt's emphasized it's a super sensitive area. For that reason, then in more recent experiments, they put a little air dam there just to get it to be a bit more well behaved, but we don't have that in the geometry. Here you see the sensitivity, and I've been trying to see, okay, there are some data, there's a cluster of data that's very close to the experiment, and then there are varying degrees of sort of length and separation zone. And I've been looking at the metadata, trying to find out if there's any pattern, and I haven't found anything yet. Why there's nothing in common between this bunch and this bunch. So yeah, I think I just have to say we concur with what the wind tunnel says. It's a hypersensitive region, and small changes have a big effect, and it's not satisfying. At least in numerics, you'd want to be able to say, okay, this is why, but I don't feel I can. Where we've looked into it, so on the right, this is a slide that Louis is going to present later. We were varying the time step, and we found that with our method, when we refine the time step, we get closer to the experiment. So we're resolving this very fine turbulence better. There's ID36, which was run with CCM+. They varied the time step in a similar degree, and their data collapses almost. So I'm super confused and super interested, and I want to ask the colleagues at Siemens if there's something special about the DES formulation which makes it less sensitive to the time step. Is Sylvain here, or no, he's not?
Not here.
He's not here, so I'll reach out to him. We can chat. Okay, I think the velocity profile's on the slant. The only thing I've noticed is that participant 2, there seems to be a processing error. All of the 0-2 data look very far away. None of the data gets this very flat and low velocity region that we see in the measurements. This is V3 just behind. When we go further downstream to V5, we see it actually, this discrepancy really crystallizes out. So none of the data here, and I'm going to then, so Burkhardt has correctly said that with, was it 17 different wind tunnels? Or yeah? 11, okay, 11 different wind tunnels, let's not overdo it. The pressure on the surface is hardly affected, and I believe that, and it's really good to know. We're now going further into the wake, and it's the region where there's some kind of confinement from the wind tunnel will be increasingly felt. There's a collector, or maybe some of the wind tunnels were, and I think that the difference between open road and the wind tunnel grows as we get deeper into the wake. And we really, I don't know if all these methods with all these different fidelity levels. So whether or not we understand why it is, and there's a question if anyone has run a realistic wind tunnel domain or tried to emulate a wind tunnel domain, that would maybe shed some light on this specific question. But this is also the value of sharing our data, because on our own, when we look at our data and we see we're miles away from the measurements, we start to go digging, oh dear, what's gone wrong. But strength in numbers. Look, there's a CFD consensus, and it's very, very different from the wind tunnel consensus, so it's very valuable. All right, I'm going to wrap it up. And first of all, thank you to everybody for this very hard work contributing these very expensive in terms of CPU, GPU, and human time simulations, for taking part in our regular meetings. I could only scratch the surface in the 30-minute slot. I could draw a few conclusions. I see that the uses for case 1 is more of a canonical bluff body flow. We'd love to understand what's going on with the base pressure better, but it's not a good case for looking at differences in boundary layer treatment, because it's just going to separate at that trailing edge, no matter what you do, whatever you get right or wrong. But case 2 is more complex, and there's more going on with the boundary layer, but it's also harder to interpret because of that complexity. So we tried to understand the differences in the results with some mixed results. There are some fairly clear findings, like the boundary layer shielding. I didn't really touch on it, but some partners have varied wide plus and found, maybe confirming earlier findings that the overall effect is very weak. And there are plenty of mysteries still here. So what's going on in the underfloor leading edge? Will that remain a mystery forever? We've got these differences in skin friction, base pressure on case 1, questions about the separation topology in the notch on case 2 and the wake velocity. Yeah, the dashboard is really, really useful. And I'd encourage everyone after the workshop to get stuck in, give us your feedback. And I think so this is my thinking, just because we've only scratched the surface and there's so much data here, there's so much more to learn. We need to throw it open to everybody and keep working, and maybe look towards a sort of a post-workshop event where we try and really firm up the conclusions. Yeah, so that's all from me. Thank you.